So now let's go to rules for oxoacids. And again, similar to the rules for binary acids, an acid is stronger if it is easy for the proton H plus to be dissociated from the Lewis structure. Okay, oxoacids have the formula HNYOM. Basically, here, Y can be any nonmetallic compound, can be carbon, nitrogen, sulfur, any halides such as chlorine, bromine, iodine, name them. And you can have here as much oxygens as we can too. I guess it's not shown here, but you can also have any number of Y's. Can be 1, 2, 3. I mean, of course, within reason. So let's look at two kinds of oxoacids. With the first oxoacid, let's look at where we have different Y's. Okay, different Y's meaning either you have different elements, but you have the same number of oxygens. Okay, and let's look at the simple system wherein we only have one oxygen. Let's look at these acids. Okay, so again, an acid is stronger if it is easy for the proton to dissociate from the Lewis structure. Okay, so therefore, as we have actually seen before with binary acids, mostly these are due to differences in electronegativities. Okay, an electronegative atom tends to actually pull shared electrons with it towards itself. Okay. By the way, it's important to remember the trend for electronegativity, which is this. If you have a periodic table, okay, that's why fluorine is the most electronegative element. Okay. So basically, if you have a more electronegative group, then its ability to pull electrons actually is higher, and therefore these shared electrons, okay, those shared electrons are actually pulled much more towards the electronegative element. So let's say, for example, here we have HOX acids, okay, in which X corresponds to different halides. Okay, so we know from the trends that chlorine is more electronegative than bromine, than is iodine. Okay, and according to Ka values, we actually see here that indeed HOCl is more acidic than HOBr and HOI. Okay, and again, that's just because chlorine can pull these electrons more to oxygen. Okay, now as that happens with chlorine having a higher electron density than oxygen, oxygen tends to pull these electrons more, okay, towards itself, so that the proton or H here, its grab of those two electrons shared between itself and oxygen is loosened. Or, I guess in chemistry terms, this bond becomes more polarized. Okay. Now, groups like this, chlorine, bromine, iodine, they're actually called in organic chemistry electron withdrawing groups, okay, or EWGs, okay. And basically, that's what they do. They withdraw electrons just because of their sheer magnitude of electronegativity. Their electronegativity values tend to be high. Now, I did say group and not elements because there are certain groups made up of more than one element which can withdraw electrons from a structure. Okay, but so that's the argument for HOCl. Now the same thing can be made again for HOBr. Bromine will still pull electrons from itself, okay, sure, but that pull of electrons is not as much as chlorine from oxygen, okay, which basically makes the pull of oxygen to hydrogen a little bit less than if this other oxygen than if that oxygen was connected to a chlorine instead of a bromine. Okay, and then the same thing can also be said about HOI. Iodine is actually less electronegative than oxygen. So there you go. And then another kind of oxoacid that we should consider will be, now what if we have different numbers of oxygen atoms, okay, and this time we have the same Y, okay. Now oxygen, keep in mind, is also an electronegative element, okay. In fact, it's the second most electronegative element next to fluorine, at least from periodic trends, okay. And the presence basically of more oxygens just introduces more electron withdrawing groups into the acid structure. So let's write that down. So the more oxygens you have, then the more electron withdrawing groups you have. Okay, that's why for these acids of chlorine, from hypochlorous acid, which has only one oxygen, okay, it is actually less acidic than chlorous acid with two oxygens. And then chloric acid, which we have defined as actually a strong acid, is actually stronger than chlorous and hypochlorous acid. Notice, by the way, that the Ka value for chloric acid is 1, okay? And perchloric acid has a very large Ka value that, again, it is considered to be a strong acid. In fact, according to this one, even stronger than chloric acid, which itself is a strong acid. Okay, so some people tend to look at this from the point of view of central atoms and their formal charges. But again, what this is just trying to show you is the more oxygen atoms you have, the more acidic an oxoacid, remember we're talking about oxoacids, is. And again, you have to compare apples to apples, so make sure that you have the same element Y, okay, whatever that Y is. Okay, and then the last acids that we should consider, and you'll be seeing this a lot in organic, will be carboxylic acids. Okay, so carboxylic acids have this formula, RCOOH, where basically you have a group here, let's call it R. I mean, it can be a long alkyl chain similar to what we have been looking at chapter 10, or basically just hydrogen, can be whatever. But it has a double bond with oxygen, this carbon that is, and then also has a single bond with another oxygen, and then H. Okay, and that's basically the complete structure of carboxylic acids. Okay, so the proton here, which is available for acid-base reactions, will be this hydrogen. Okay, and now this time you have two groups again, which are contributing towards the pull towards electronegativity. So we have this oxygen, which is withdrawing these two electrons from hydrogen. Okay, there's a net polarity pointing that way. And then this oxygen doubly bonded to carbon also has a polarity pointed towards oxygen. Now, when a carboxylic acid gives up this proton in an acid-base reaction, then you form the carboxylate ion, okay, which basically has this structure, okay. Now, from this structure, which has, let's make this clearer, 6 lone pairs around it. From this structure, you can actually draw another resonance structure. So let's say, for example, here we have acetic acid. So this is the structure of acetic acid. Okay. Now, when acetic acid actually forms the acetate ion, again, you can write resonances within these 3 elements. And what we can see here is actually we can write 2 resonance structures for the acetate ion, but we can only write 1 for the acetic acid, the actual carboxylic acid itself. So therefore, the acetate ion, okay, the acetate ion is resonance stabilized. Okay? In other words, the acetate ion is actually, sure, still a weak base, but it prefers to actually exist. Okay? Anything with more resonance structures actually are stable, as you will actually see in organic chemistry. Okay? But again, because the acetate ion has more resonance structures, or has resonance structures to begin with, then it is a stable compound. Okay, and because of that, it just means that acetic acid, in order to form the more stable acetate ion, is willing to give up that proton. Okay. Now, trends for carboxylic acids. Basically, if you introduce electron withdrawing groups to acetic acid, such as, for example, chlorine, then you increase its acid strength. Okay. Remember that for pKa values, the lower the pK is, the more acidic a compound is, which basically translates to higher Ka. And here, for the series, the more electron withdrawing groups that you have, the more acidic an acid is. Okay?